Let us look at trigonometric series. But before we proceed with trigonometric series, let's figure out an important result. A simple expression to evaluate cos theta plus I sin theta to the power of n, where n is an integer. So to begin with, let's take it as positive numbers, n in n sub naught. Now applying the binomial expansion, we get cos theta plus I sin theta to the power of n is equal to nc0 times cos n theta times I to the power of 0 times sin to the power of 0 theta plus nc1 times cos to the power of n minus 1 theta times I to the power of 1 times sin to the power of 1 theta, and so on. Simplifying it by handling the imaginary numbers, we get I to the power of 0, 1, sin to the power of 0 theta 1, I to the power of 1 is I, sin to the power of 1 theta is sin theta, I square is minus 1, I cube is minus I to the power of 4 is 1. Let's simplify this further by taking care of these negative signs and all that. We get nc0 times cos n theta plus nc1 times cos to the power of n minus 1 theta times I sin theta minus nc2 times cos to the power of n minus 2 theta times sin square theta, and so on. Now that we have this, we will group the even and odd powers. So when we do that, we get cos theta plus I sin theta to the power of n is equal to nc0 times cos n theta minus nc2 times cos to the power of n minus 2 theta times sin square theta, and so on, plus I times nc1 cos to the power of n minus 1 theta times sin theta minus nc3 times cos to the power of n minus 3 theta times sin cube theta, and so on. So we are grouping the real part and the imaginary part separately. So in the compressed form, we can write it as cos theta plus I sin theta to the power of n is equal to summation r equal to 0 to n of the binomial coefficient n choose r times cos to the power of n minus r theta times I sin theta to the power of r. We end up with real and imaginary part. So let's focus on the real part first. So let a sub n of theta equal to nc0 times cos n theta minus nc2 cos to the power of n minus 2 theta times sin square theta, and so on. A sub n of theta is equal to the summation k equal to 0 to the floor of n by 2 of the binomial coefficient n choose 2k times minus 1 to the power of k times cos to the power of n minus 2k theta times sin 2k theta. Now, why do we have that floor of n by 2? Since we have even powers, 2k is going to be between 0 and n, which means k is going to be between 0 and n by 2. Now, k must be an integer, and the largest possible k is the floor of n by 2. Okay, now let's look at the imaginary part. So let b sub n of theta equal to nc1 times cos to the power of n minus 1 theta times sin theta minus nc3 cos to the power of n minus 3 theta times sin cube theta, and so on. So b sub n of theta is equal to the summation k equal to 0 to the floor of n minus 1 by 2 of the binomial coefficient n choose 2k plus 1 times minus 1 to the power of k times cos to the power of n minus 2k plus 1 theta times sin to the power of 2k plus 1 theta. So therefore, cos theta plus I sin theta to the power of n is equal to a sub n of theta plus I times b sub n of theta. Now here, remember, a sub n of theta and b sub n of theta are real valued functions of theta indexed by integer n. Now, cos theta plus I times sine theta to the power of n plus 1, we are taking the next power, is equal to cos theta plus I sine theta times a sub n plus I times b sub n. So cos theta plus I sine theta to the power of n plus 1 is equal to, and we do a normal distribution, a sub n cos theta plus I times b sub n times cos theta plus a sub n times I sine theta plus I square b sub n times sine theta. And again, grouping the real and imaginary parts, we get a sub n cos theta minus b sub n times sine theta, because I square is equal to minus 1, plus I times a sub n sine theta plus b sub n cos theta. So what have we achieved? So the real imaginary decomposition is closed under complex multiplication. That's a very important conclusion. Now let's look at the initial conditions. So cos theta plus I sine theta to the power of 0, that is going to be equal to 1, which implies a sub naught equal to 1 and b sub naught equal to 0. Because remember, cos theta plus I sine theta to the power of n is equal to a sub n theta plus I sub bn theta. So when n is 0, what happens? This is a sub n will be 1 and this will be 0. Only then will this be equal to 1. Okay. Now cos theta plus I sine theta to the power of 1 is equal to cos theta plus I sine theta. That means a sub 1 is equal to cos theta and b sub 1 is equal to sine theta. Now we have taken care of the initial conditions, that is when n equal to 0 and n equal to 1. So defining for all n in n sub naught, cos n theta will be equal to a sub n of theta and sin n theta will be equal to b sub n of theta. Now confirming the recurrence cos n theta and sin n theta by substituting the definitions, cos x plus y is equal to cos x cos y minus sin x sin y, and sin x plus y equal to sin x cos y plus cos x sin y. So we are going to verify this, taking x equal to n theta and y is equal to theta. We get cos n theta plus theta is equal to cos n theta cos theta minus sin n theta sin theta. Sin n theta plus theta is equal to sin n theta cos theta plus cos n theta sin theta. So here this can be written as theta times n plus 1. Here again theta times n plus 1. That means these two are going to be a sub n plus 1 and b sub n plus 1. So a sub n plus 1 is equal to a sub n cos theta, because look at the definition, cos n theta is equal to a sub n of theta. So a sub n cos theta minus b sub n sin theta and a sub n sin theta plus b sub n cos theta. So this agrees with the previously derived recurrence. So the definitions are consistent. The initial values match. The recurrence relation matches the standard angle sum formulas. For every non-negative integer n, cos theta plus I sin theta to the power of n is equal to cos n theta plus I times sin n theta, where cos n theta and sin n theta arise naturally as the real and imaginary parts of the binomial expansion. Here, a sub n of theta and b sub n of theta are the nth term of a sequence of functions. The series a sub n of theta and series b sub n of theta is a series of functions. A of theta or b of theta is a single function, and a sub n or b sub n is a numeric sequence. Quite abstract, right? But the most important point is that we have arrived at a simple expression to evaluate cos theta plus I sin theta to the power of n. That is cos n theta plus I sin n theta. But remember, here we have only shown this for n in n sub naught. Now we have to show it for the negative integers as well. Okay, so that is what we are going to do in the next session, and then we would have shown that cos theta plus I sin theta to the power of n is equal to cos n theta plus I sin n theta for n in z, that is in the set of integers. Now, if you found this session helpful, please do share, like, and subscribe. Comments, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.